Diffraction is the spreading of a wave around the edges of an obstacle or through an opening. So consider this opening, which has some width A, and we have a planar wave propagating through this opening. So for simplicity, we consider the light source sufficiently far away such that the wave front becomes flatter and flatter as we move away from the light source. And we'll consider a monochromatic light source, such as a laser, where the light emanating from this light source has the same wavelength. So for example, a visible red light. So as this planar wave encounters this obstacle, part of it's going to get blocked, and therefore we expect a single bright spot to be seen on the screen at the other end. But this doesn't happen due to the Huygens-Fresnel principle, where each point on the wavefront is a source of spherical wavelets. So note that there's an infinite number of sources of spherical wavelets on the wavefront. So as these wavelets propagate and interfere with each other, the wavefront progresses as follows. So in the middle, we have constructive interference between the wavelets, and on the edge, there's no other wavelet to interfere with this one. So the wavefront now looks something like this. So it's being bent or diffracted due to the top part of it being blocked when going through the opening. And then as it progresses, it looks something like this, and so on. So here the wavelength is sufficiently smaller than the gap size, but on the other hand, where the wavelength is larger than the gap size, then these diffracted waves will be spherical. So the interference pattern here, due to the interference of those wavelets, consists of bright and dark spots on the screen. And this is a plot of the light intensity, which is the highest in the middle and drops off as we move away from the middle of the aperture. And we'll analyze this in a bit more detail. Let's come up with a mathematical relationship to describe the diffraction patterns due to a light wave with a wavelength lambda going through an aperture or a slit with a width A. So on this screen, we're going to see a bright spot followed by a dark spot, and then a bright spot gets smaller as we move away from the center of the screen. So here we have a dark spot followed by another bright spot. So considering this plot of the intensity of light along the screen, then at the first minimum, where the first dark spot is, the different points on the wavefront must be paired up to interfere destructively. So for example, the wavelets from these 2 points travel the following distances. So these are the light rays. And for destructive interference to occur between these 2 wavelets, the bottom one must travel an additional distance of lambda on 2 compared to the first wavelet. So if we blow up that triangle, it'll look something like this. And this distance here is half the width of the aperture. And this angle theta is the following angle between the horizontal and this line to the minimum. So as revision, we can visualize constructive interference here, where the waves are in phase. So if this wave over here move the full wavelength, then we again get constructive interference. But if the wave moves by half a wavelength, then we get destructive interference. And here we assume this angle theta is roughly equal to this angle theta, because the distance to the screen, being L, is quite large compared to the width of the aperture. So this angle is really going to be quite small. So now using trigonometry, we have sine theta is equal to the opposite, being lambda on 2, on the hypotenuse, being the width of the aperture on 2. So if we multiply through by a on 2, we get the following expression. So note that these two wavelets destructively interfere, and similarly another two wavelets will destructively interfere in a similar manner as they arrive at the screen out of phase, and the remaining wavelets on the wavefront will destructively interfere to get that dark spot at that point. So more generally, if we look at this second minimum and do the same thing, the distance that these wavelets have to travel gets larger, and therefore the distance between their paths to get destructive interference is going to be 3 lambda on 2. So more generally, this expression becomes a on 2 sine theta being equal to m lambda on 2. And given that these 2's cancel, we finally obtain the following expression. So this is for the case of destructive interference. And note that m is a positive integer corresponding to those minimums, representing the dark spots, because we could have chosen any two wavelets to destructively interfere. So for example, the wavelet starting from a on 4. Now if we take y min as the distance from the center of the brightest fringe to each of those minimums where destructive interference occurs, then in general we have tan theta is equal to y min being the opposite edge on the adjacent edge, being the distance to the screen. And for a small angle, which is less than 10 degrees, then tan theta will be approximately sine theta. And therefore, using this relationship, we have the width of the aperture by y min on L being equal to m by the wavelength of light. And if we turn this equation around, we have y min is equal to m lambda L on A. So for m is equal to 1, we get this distance, and then multiplying this by 2, we can obtain the width of the maximum bright fringe. Now the locations of the maxima are approximately halfway between the destructive points, so you won't get a formula that gives an exact location as we did for the destructive points. Let's look at this simulation that shows that the diffraction pattern produced by a wave passing through an opening depends on the shape of the opening. So for example, for a circular opening, we see that the central maximum fringe is a circle, followed by a dark spot, and then a ring, and so on. And the intensity drops off as we move away from the center of the aperture. And if we increase the diameter of the hole, as expected, the central bright fringe gets smaller according to the formula that we derived, that described the distance from the center of this fringe to each of the minimums, being the dark spots. And that's stated that this distance y min is inversely proportional to the width of the aperture. So as we can see, the smaller the aperture is, the larger the central fringe is. And if we increase the eccentricity to an ellipse, then we can see that the fringes become elliptical and behave in much the same way. And if our aperture is a square, then similarly, you get a maximum central fringe, but this time it's a square, followed by a dark spot, and then followed by rectangular fringes, with dark spots in between them. And the intensity of these fringes drops off as we move away from the aperture. And if we increase the width, the central fringe becomes narrower, as expected. So this is similar behavior to the circular aperture. And increasing the height does a similar thing. So I'll leave a link to this simulation in the description so you can experiment with it. An incident beam of light with the following wavelength goes through a single slit with a width of 2 mm. Now it hits a screen at the other end, which has a distance of 8 meters from the slit. And in part A, we're asked to find the width of the central bright fringe. So recall our formula for destructive interference, which was A sine theta, is equal to the index m multiplied by the wavelength, where m equals 1 marks the first minimum, m equals 2 marks the second minimum, and so on. And recalling that y min was the distance from the center of this fringe to each minimum, then the tan of this angle theta was equal to y min on the distance to the screen. And then using our small angle approximation, tan theta was approximately equal to sine theta, and we derive the formula y min is equal to m lambda L on the width of the aperture. Now given we're looking for the width of the central bright fringe, then the distance from the center to the first minimum is obtained by taking m is equal to 1. And lambda is the wavelength of light, which is given in nanometers. So we multiply by 10 to the minus 9 to get that in meters. And the width of the aperture, or slit, is given as 2 millimeters. So we multiply this by 10 to the negative 3 to get that in meters. And here, L, being the distance to the screen, is 8 meters. So if you calculate this out, you'd get y min is 2.488 by 10 to the minus 3 meters. So if you multiply this by 1000, you'd get y min as 2.49 millimeters. And therefore the width of this bright fringe, which will denote W, is equal to 2y min. So that gives 4.98 millimeters. And in part B, we're asked what happens to the width of the bright spot if the width of the slit is increased. So as we can see, as A is increased, the width of the bright spot gets reduced.